Hello and welcome everybody to our video presentation for the Unsure workshop at MICAI. We've all used some sort of classification methods for problems, for example to detect hemorrhage-affected brain 2D CT scans. However, during development the boundary will be trained under ideal cases, where labels are provided and where classes are balanced, which is not the case in reality due to the low incidence rate of diseases and the challenge of collecting clinical data of such diseases. So we have an inherent data imbalance, right? And under this data imbalance, such models fail. To address this, unsupervised methods emerge as a popular solution, which solely depends on the abundantly available data of healthy cases. Density-based methods, which explicitly model our data density, seem most theoretically justified, where test samples with lower log likelihood, i.e. falling outside our training-in distribution, will be flagged as OOD. And in spite of this reasonable assumption, where we assume higher likelihoods for in-distribution samples, past work has shown that deep generative models trained with MLE assign lower likelihoods to in-distribution samples. And to address this, it can be argued that the in-distribution samples aren't necessarily likely, but typical. Past work has investigated this for some benchmarks, and our work extends the notion of typicality-based OOD detection towards the clinical domain. Given a set containing all possible sequences of n IID samples, and a typical set containing samples that satisfy the following relation, which basically says that the empirical entropy of the typical set will converge to the entropy of the source distribution. And it's important to note that this is not the most likely sequence. And to illustrate this, we provide a counterexample. Given a biased coin toss, where the probability of heads is 0.8 and the probability of tails is 0.2, most people would assume that the typical set is the most likely set, i.e. so a sequence containing only heads. But this is false, as if we compute the information content of this most likely sequence, we see that it will never converge to the entropy of our source distribution. We can extend this to high-dimensional data, as we're working with images, right? For a d-dimensional Gaussian, the typical set will reside at the radius of square root of d, and not at the mode, so not at the most likely point, as defined by the Gaussian anomalous theorem. And we can try this for ourselves, right? If we sample an image from a unit Gaussian, how often will you get an all-gray image? The typical sampled image would be noise, matching the entropy of our source. Typicality can be quantified using the following metrics. The TTL measures the distance from the typical set in latent space, and samples are flagged as OOD when it falls outside of the typical set. On the other hand, we have the gradient score, which juxtaposes typicality with the probability mass. The typical set resides at high probability mass. This is due to the volume density relation of a high-dimensional Gaussian. So a high gradient would mean that the sample is not in a space of high probability mass, which we then would flag as OOD in that case. The proposed method uses GLOW with standard parameters, and our loss function is adjusted to penalize high scores for in-distribution data. This is also done for convergence, but also to avoid score flipping during training. We train our models on benign images, and for the proposed method, we evaluate on the gradient score metric. We use 4 different datasets with 3 different modalities. All images are resized to 128 by 128 pixels. So the results, looking at the quantitative results of the proposed method, it does perform quite well. Except for the head CT dataset, the proposed method significantly improves upon the dataset specific state-of-the-art models, and the log-likely-based glow evaluation, and also the evaluation using the TTL. Looking at the most likely samples of the ISIC dataset, we see minimal diversity with similar lesion size that are centered and have the same pigmentation, whereas the most typical samples show higher variation, which is in line with theory, matching or approximating the information content of the source. The least likely samples show an intrinsic bias of textures, which are hairy images in the case of the ISIC dataset, which also matches findings of previous work. The least typical samples seem to capture the malignancy more. We show the superiority of typicality over likelihood evaluation for medical images, where we outperform certain state-of-the-art models. We also show a reduction of the intrinsic bias for textured images, and also the robustness against data imbalance of a proposed method. For more information, please refer to our paper. Thank you all for listening.